sounds pretty cool.
I'm going to, I guess, major change. I'm graduating this semester. I'm going to come back for my physics degree to be an astronomer.
Sweet.
Yeah.
Okay. That's what
It's at 360.
Anyone else? How did you hear about this? This is not a normal class. In fact, most universities don't have this because I made this class.
So when I took life need, or not life need first. Yeah, I took both, but I remember hearing about this class because usually when it's not COVID, y'all go to a trip at the end, right? But you know, I still wanted to take it. Yeah.
Yeah, for I must have been 8 years in a row, I've taken this class on a trip. We go to New Mexico, or we would go to New Mexico. We rent a bus. At first, the class was small, and we take a van, and it was, you know, rectangular van. But then we got better. I don't know. We got bigger, and we got more sophisticated, so we had chartered buses and everything. So it was really nice. Somebody else had to drive it for me. But yeah. So last year, of course, we actually had it all scheduled. We had the hotels and the bus and everything, and then all of a sudden, spring break, they said, "Oh, nobody's coming back," and we had to cancel. This year, I don't think there's any way it's going to happen. We usually do it the last weekend before, but not the one right before finals. So usually it was around the 25th of April, somewhere in that range. I didn't want to do it on the very last one because people were getting ready for finals and all that. So we do it the one before. We wanted to wait as long as we could because when you go to where we go in Chaco, it's about 5,000 feet elevation, and you still get snow. We got snow down one year. There was like 4 inches of snow that we were driving through. We make a snowball and have a good time. So you try to go as late as you can. But right now they're not allowing any travel for anybody. You know, I should say emergency travel only. So you have to be approved to go. Well, guess what? We're not anywhere close to being approved. So unfortunately, that's the way it is now. If next year I teach a class, we only teach in the spring. If next year we can travel, and if I have a smaller class, because we usually rent a bus that'll take 50, but the class usually back. If you took the class this year, but you wanted to come just on the trip next year, we could make that happen. Okay? To a point, you know, it depends on how many people are doing it. But that's the way. The people in the class get first priority, and whatever seats are left will be former students. And then if there's still seats left, then I give it out to things like other faculty stuff that come along with the class. So, yeah, but that is the situation. Now, I also got bad news because I told the people last spring they could do the same thing too. So, but that's 2 years ago. By next year, so more girls will probably be graduated or forgotten. All right, but yes, so no trip this year. Just like a regular one. Okay. Anybody else? Why they taking the Archaeoastronomy? How many wanted to have astronomy minor? What's your astronomy minor? You do. Yeah, we don't have astronomy major. Yeah, you know, I would love to have one too. That's what I am as an astronomer. But it's also you have to get approval. It takes many years, and we have to show the demand, and that would be tough to do. But what's that? Yeah. Well, that's all the whole thing. You have to say, well, we have this many students. We have this many students. Faculty should cover these classes so that these students can do it and all that. We have to get approval from the board and from SAC, which is the accrediting agency. And so whenever you want to go do a new major or a new program, it takes about 2 to 3 years to get it approved, if everybody's happy. So, yeah. When I first came, they didn't even have astronomy minor. In fact, they were teaching, one physics guy was teaching one astronomy class that was called like Physics 260, so nobody even knew it was astronomy. And so I kind of created all the astronomy classes you see now were created by myself and Dr. Williams. He came about 4 or 5 years after I was here. I'm like, well, we need more people because I started teaching hundreds of students with semester. It was too much. And so when he came, then we started doing all that. And so now we have like 8 or 9 different classes. We have an astrophysics emphasis. It is a physics major, but we don't have an astronomy major. Okay. Now you don't really have to do that if you want to be a professional astronomer.
What do you have to do? Because I feel like I have to take physics.
Yeah, you do. Physics and math is the best thing because once you get to grad school, then you specialize in astronomy. That's the way I did it. My undergraduate degree was in physics and math. I got a double degree in physics and mathematics. And then when I went to grad school, I went into astronomy. Okay. Because really, astronomy is just physics applied to space.
Yeah, because I was wondering what the stuff I have to take.
That's one way to go. Yeah. I mean, you can go with an undergraduate degree in astronomy. Bigger schools have that, like UT Austin has it. There's a handful in the state that do that, but physics way is just as good. In fact, sometimes in some ways you do better in grad school because you got a slightly better background, and a lot of it is the math and the physics. Yeah, if you can understand that well, the astronomy is just learning about the specific objects. All right, so let's talk about syllabus. Reminder, yes, we're going to meet, and this is a face-to-face class. So we will meet here every time. And yes, not wear a mask every time. Class. If you don't have a mask, you're not going to be allowed in the class. And just try to be safe. And it's easier for me if you kind of always come in and sit in the same seat you're in right now. That's fine. I mean, I'm not saying you have to be in that seat, but it's easier for everybody if you just kind of come through the seat that you're in. If you don't like that seat, yeah, you can move around, but it's basic idea. All right, so class hours are here, 2 to 3:15 in this room. Usually, this is the other thing that changed, usually we meet in the planetarium because I prefer teaching in the planetarium. But the planetarium only allows you to have 16 with COVID. And that's not enough. So that's why we're meeting in this classroom. We may still use the planetarium. I just haven't figured out how to get 22 people in when they only allow 16. We may do something like a split a day, like on a Tuesday, or actually usually the planetarium shows are only like 30 or 40 minutes. We might say, okay, half the class at the beginning goes there, watches something, and I'll lecture in here for the other half, and we'll swap. That would make about an hour 15 class. So we may do something like that. I like to use the planetarium. I can use it a lot. Normally, we won't be able to do it as much this time, but we'll do what we can. Okay, just want to let you know that I may announce, hey, we're going to be in the planetarium, and we'll go in there and do some demos, and there's some good shows that actually fit well with what we're doing. My name is Dr. Montgomery. My office is room 106. As you come in the front glass doors, go left. It's the second door on the left. Third door on the left. It's the department office. I'm the department head, so it says physics department, so my office is right in there. Okay. If you need to see me, email is the best way to get a hold of me. Okay. You can try to phone me, but that's usually not good. Sometimes I check messages and I realize I haven't checked them for 2 weeks or something. So email is good. I check my email all the time. During the week, I'm on it all the time. So I guarantee I'll give you an answer within 24 hours during the week. Now, if you email me on a Saturday, I may not look at it until Monday morning. Because, I'm like you on the weekend. Sometimes I like to just take a break. But I guarantee during the week, I will check the emails and I will get back to you within 1 day for sure. Okay? And most of the time, within a few hours, I'm on it. Because that's pretty much what we do nowadays. Is we're online all the time. So that's the best way to get a hold of me. If you want to set up an appointment too, I'm happy with meeting with you. We can either meet face-to-face or we can meet by Zoom or a phone call, whatever works for you, okay? So I'm flexible with that too. My office hours are Monday, Wednesday, Friday at 11 to 12. That's when I plan to be here. But I understand it doesn't always work for people. So if you say, hey, can I come see you another time? It's like, yeah, sure, we'll just set up the time. That's not a problem, okay? I try to be accessible as possible to all students. So if you need something, just let me know. We'll make it work. Textbooks. This has one required textbook. It's this one right here. Has anybody bought the textbook? How much did it cost?
Like
50?
Yeah.
Okay. You see, I thought it was a month. Okay. But when I decided to create this class, like I told you, I created this class on my own. There are some other universities that have an archaeoastronomy class, but almost all those approached it from a different point of view. They approached it from the point of view of archaeologists that put astronomy into the archaeology. Now, being an astronomer, I kind of told you the opposite way. I'm saying, oh, I'm an astronomer. So what I do, and what we're going to do in this class, is we learn about astronomical things like how things move, what we see, why we see it that way. And then we look at ancient sites and say, okay, do we see any sites out there that shows they understood the same thing? So we approach it from the astronomy side. You learn the astronomy, then you find the site. Most of the archaeology ones say, oh, let's talk about this site, and they go into all the depth of the site. I'm not going to spend a lot of time on that. Like when we're going to talk about the Mayans and stuff like that, we're going to talk about their astronomy and their calendars. So we're not going to talk about how they live day to day and their political structure and how they died. That is for an archaeology class. Mine is always about, okay, what astronomy do they have? And how does it relate to them? And how do we see it? How do we know that they have that information? Okay? So that's why we approach it that way. That's why I couldn't find a textbook that matched the way I wanted to teach it. So what I did is I created the class using a whole bunch of different books. These are all different archaeoastronomy type books. And you see, I pulled stuff out of all of them. I tend to mark everything I do so you can reference it. At one point, I was going to write my own textbook. I got through about 2 chapters and then I read it. It takes a lot of work to write. If I had more time, I might just do that, but I don't know. Maybe when I retire, I'll write an archaeoastronomy textbook. But there are things or are readings in some of these that I expect you to read. Okay? A lot of them, or I should say it, some of them you can get the readings and stuff online. If not, they are in the library. Okay? And they're on reserve in the library, these books are. So you don't have to buy them. Okay? But if I say, oh, you need to read this, then you just have to go to the library, and since it's on reserve, you check it out, you read it right there, and then you can check back, you can't take it out of the library. But most of the things are like, oh, read 20 pages in a book like this, it'll take you like 10 minutes. Read this story or something like that, okay? So that's why I have a listing of all these other books on here. And to go along with that, there's a few of them that are going to be required readings, but most of them, I put these down if you just want to learn more. If you're interested in more material, it tells you the book, which book it came from, what pages it's on. So I'm going to give you this too. This is the reading assignment. I also, if you like lose this sheet, if you go to D2L, I put this information on D2L too, so you can get the syllabus and this as well. So that's why there's so many textbooks. Now this textbook, the Sky Watchers, you need to buy this one. Okay, you need to have this one because we're going to reference it. In fact, you need to bring it to your test because there's charts in here. There's a couple of charts that we will use when we are doing figuring out things. Okay, so you need to have the Skywatcher book. This book right here. Met this guy, talked to him. He was up at Colgate University in New York. Nice guy. He's retired now, but he kind of approached it. He was the closest one to approach it the way I did, but he was more of the astronomy side. But he still was focused. He got very focused on very specific cultures. He was very much Central American, which was cool. That's my favorite part. That's the most interesting, in my opinion.
Did you travel a lot as an astronomer?
I have. I've been all over. Yes, there's still a few places I want to go. Of course, everybody has their bucket list, but yeah, I've been to every continent except Antarctica. Yeah. So, been around, and yeah, and been to many of the places that we'll talk about. There are some I still haven't been to that I want to. Machu Picchu, I still have not been to, and I still want to. Places like that, but yeah, you know, I've been to Stonehenge, I've been to the Mayan ruins in Yucatan, all kinds of cool places. Yep, a lot of fun. And one of the advantages being astronomer is most of the time I traveled, I didn't have to pay for it. Somebody paid for it. And it's kind of weird because you would go to conferences, you get to go to a conference about once a year. Most people would pick a conference because of what the conference was about. I would go and say, okay, if there's a conference in the place I want to go, I don't care what the conference is about. That's the conference I'm going to because I want to see the spot. All right, more stuff. You need to have a compass. Okay, not this kind of compass, not this kind of compass. Yeah, no, yes. We'll talk about the other one too. You need a compass and a straight edge and a protractor. Okay. You can get them at the bookstore. They cost like 3 times as much when you go to Walmart. And I think you can get a protractor for like 89 cents at Walmart. Okay. The good thing is now too, with most classes online, they don't sell out. Lots of times with high school concessions, I guess they buy them up or something. You just can't find them, but I think they still have lots of them. I try not to go shopping. But yes, you need a compass, a straight edge, and a protractor. Okay. I want you to have the compass and the straight edge by Thursday because we're going to talk about this. Why do you need this? Because we're going to talk about how the ancient people used a compass and a straight edge to determine angles and how to lay things out, like especially the Egyptians. They laid out their pyramids nearly perfectly north, south, east, and west with just a compass and a straight edge and the stars.
And it's earthquake.
Yep. So you don't have to have one that's fancy. Okay. There are cheaper ones. I have had problems with cheaper ones in that what happens is as you're like moving around, it tends to fall apart. And if you don't keep the angle exactly right, then it defeats the purpose of having a compass. Right? The whole goal of a compass is to make sure that that distance there, whatever you set it to, will stay that distance. So I understand. You might have one already. Most people, maybe. Did you have to get one for like a geometry class or anything? High school? I got something. Yeah. This one I got at the bookstore. I think it was like $25 to $30, so it's pretty expensive. Okay. It's more of a drafting level one. Okay. So yeah, when I'm saying you don't have to have one this fancy, you can also get them off Amazon. You just gotta get it here fast. Okay. All right. You got Prime. You could probably get it here by. You order it this afternoon. You can have it by tomorrow. All right, and a protractor. Any protractor will do. Okay. We're going to make a lot of drawings. And so the more accurate you are, the better you're going to understand it, and it's going to make more sense to you. Okay. Because it's all about what's going to happen where, right? Yes, sir. Think about it this way. Think about, remember, don't use any of your knowledge that you have from living in the 21st century. Okay? Or 22nd. 21st century. They keep changing now. So, what kind of things would you do? If you knew astronomy or ancient person, how would you show that?
If I knew what?
Imagine you're somebody 5,000 years ago. What things would you look for? What astronomical events would you look for that you would try to display using your buildings? And your buildings pretty much had to be in stone because that's the only thing that survives. If you build it out of wood, 5,000 years, it's gone. Mm-hmm. So almost everything we're going to talk about are ancient stone ruins. Well, what kind of things would you look for? Okay, but I meant like what kind of astronomical?
Constellations.
Okay, that's good. Star alignments, because that's something that you could say, oh, this star is going to rise at this point. It's going to rise at this point all the time. Okay. What other things? Moon phases, good. Planets, yes, yeah. The Mayans are very much into Venus. What's the biggest one?
The sun.
The sun, yeah, the sun. The position of the sun changes throughout the year, and understanding that helps you to have a calendar. They didn't have anything counting the days for them. So they had to have some way, oh, when do I plant crops? Right? When do I celebrate, winter solstice or something like that? Okay? So they would learn these things just by observation and figure out, oh, on this day the sun rises here. On this day it rises here. On this day it gets this high, but in the summer it gets this high. Those are the things we're going to talk about. And that's why you have to be able to use a protractor and compass to figure out, okay, we say at this latitude, at this position, it's going to be at this height. Then we go look at the buildings and see, was there anything that looks like it matches that? That's the only way you can tell. A lot of the cultures we talk about had no written language. Stonehenge is the most famous archaeoastronomy site. They were Stone Age. There was no written language at all. In fact, they weren't even using metal tools. So all you can do is look at how they lined up their stones. And then we do a lot of guessing. That's the biggest difference between archaeology and astronomy. Astronomy is all about the evidence, right? You can make up anything you want, but if it doesn't match what the real world looks like or the real universe looks like, it doesn't matter. But archaeology, you can say, well, maybe they did this. You still have to match what we have, but there's a lot of room for speculation, right? So that's why in this class too, whenever we talk about alignments and stuff, I'll say, this is what we know. This is what we interpret. Those are different things. And you got to approach all the world like that, right? Because you get these people all the time that are saying, oh, this is the way it is, but really they're saying, this is my interpretation of the way things are. And that's very different than the way things actually are. You got to separate the facts from what they believe or what they interpret. All right. Back to the, don't worry, this is the way I teach. I go off on tangents all the time. But eventually I come back, really, usually. Class format. As you know, I already told you this is going to be a face-to-face class. All assignments will be doing and all the tests will be in here too. There's not going to be any online. But online, there is an online B2L, but it's just for looking up your grade. So I'll put all the grades on there. And helping you study for the test. Because I use a lot of PowerPoints, and on the test there'll be pictures. So I'll just put up a picture, and I expect you to recognize that site. Okay. To study for that, that's why I put the PowerPoints that I use up there. But there's no me talking, so you would never hear it. So it's hard to say, oh, I don't know what that is, because it's just a picture if you aren't there. So just come to class. I don't like online classes. I tried last semester to do online classes. I hated it. Students did worse. I didn't enjoy it. I'm like, nope, I'm going back to face-to-face. And I think we can do it safely if everybody just wears a mask and does everything like they're supposed to. I think we'll be good. All right. Homework and activities. We will do homework. I just will hand it out. It's old-fashioned. I give you a sheet that has questions on it. You turn it in the next class. Okay. We may do a couple of activities as well. Again, there's some challenges here. COVID time and stuff. We have a couple of activities that I usually do. One of them when we go outside and we use sextants. You know what a sextant is? Old captains used to use on ships to figure out the altitude of the sun or plan to figure out stars and to figure out where they are. Yeah, a telescope and yeah. And it's just really making better angles. And we have about 10 of them, I say, that we can use. And I usually take people outside and we spend one day just saying, oh, hey, let's measure the angle between this telephone pole and this. And then we measure the altitude of the sun, because that's a big deal, figuring out where the sun's position is too. But I want to make sure we can do it safely and not worry about people getting COVID. I'll probably wait and do that later in the semester because it's warmer. We also usually do an activity, and those are outside, which helps a lot. If you read the studies, when you're outside, if you're outside and you're wearing masks, the chances of getting COVID from somebody is almost zero. Okay, because the airflow gets rid of the droplets and things like that, especially if you're wearing a mask. Okay, it's being inside in closed places that's the problem, especially in closed places when you're close together. Now, I read a thing just the other day about the top 10 worst ways to get COVID. Number one, you go visit a sick friend, which makes sense. If they have COVID, you go visit them. Number two is hugging people. Number 3 is going to a bar, which makes sense. You're hanging out, and they usually have bad airflow around people like that. Number 4 was going to a gym. Now, not like our rec center, they do a good job, but gyms where people are exercising, they tend to expel more droplets, and it hangs around in the air, and it's much worse. So you don't go to your gym. Number 5 is actually going to church, because you're in a small area with a lot of people, things like that. So universities are actually really good, because we usually have big rooms, small people, so you rarely ever get it from class. Now, universities are a problem, because the students at night don't follow the things. They go hang out with each other, and they go party, and that's how everybody gets it. In class is very hard to get it, because we do a decent job, but that is the biggest problem. It's the socializing. People socialize. It's the same thing with families too, right? You're like, oh, it's our family. I'm okay. You don't wear masks and do anything, and then everybody gets it. So, I had a friend that hung out with his family over Christmas. They all got together. Well, one of them was sick, didn't know it. Every one of them got it. All 10 of them came down with it. So it was kind of rough. Now, none of them got real bad, but they're all in quarantine still from Christmas, waiting to get negative results. All right. By the way, now I'm back. I'm sorry. Off on tangent. I'm back again. No makeup activity. So if you miss the day we do that, you just miss it, because we're not going to, there's no setting it up and doing everything. So if you miss the days, yeah, I was going to say we have another activity where we try to calculate north and south using the rising and setting positions of the sun, which is kind of fun too, like the way that ancients would do it. I usually do that around the 1st of February, so we'll see how that goes. But if you miss those days, you're just out of luck, okay? Now the homeworks and those assignments all come together. I dropped the lowest one. So if you miss 1, it doesn't hurt your grade. If you miss 2, then it starts to affect your grade. So just don't miss, okay?
Yes, sir.
Project. At the end of the semester, there is a project you have to do. Because by this point, by the end of the semester, you will know all about archaeoastronomy, right? You'll be experts. And so you have to design, and I usually bring the one I designed, but I forgot to bring it in today. Actually, hold on. I'll go get it. It's only right around the corner. I'll be right back. Here's my project. So what you have to do, and by the end of the semester, you'll know how to calculate all kinds of things like where things rise and set, how high to get, those kind of things. And then you have to create some kind of creative story about whatever project, you know, it could be someplace in the past and you're just talking about the ruins, or it could be someplace in the future or present, whatever you want, you got to create some kind of story. Has to have astronomical alignments, right? And then you have to do a presentation on it. And you have to make a model of it to show everybody. So you get up here and you say, all right, this is it. So my backstory is that we know the Earth is going to, and all humanity is going to be destroyed in the next about 2 years because a giant comet's going to come and kill us. And the government came to me and said, here, I want you to build something that's going to survive the comet killing us, so that aliens from the future, when they come to Earth, can know that we knew astronomy. So I'm like, okay, I can do that. So this is the design I came up with. So this is going to be really big. This is going to be like 30 feet tall, about as tall as this building. And you're going to have these arcs going across here and arcs going this way. And it's going to be lined up. If you look here, north is actually this way. I did it diagonally so I could fit more on here. And if you come and you stand at the center there where all the lines come together, you look directly over this line, there's actually a slot in the middle of this line. That points exactly to the north celestial pole of the Earth, which is key, which we're going to talk about a lot, and it's keyed by your attitude. Then, these paths here, right here, are the path of the sun on different days of the year. So this is the path of the sun, the lowest one here on the winter solstice. This way you can see better. This is on the equinoxes, and this one is on the summer solstice. So the maximum the sun gets is that one, the minimum it gets is that one, and then it goes back and forth in between. Each of these marks is 15 degrees apart because the sun or the earth rotates at 15 degrees an hour. So if you look at where the sun is, it's this like giant sundial as well. And then while you're sitting here, you look on the edges, there's lines on the ground. This line right here, not the red one, but the other one, you can see the color, that's the maximum sunrise position. That would be winter solstice. That's as far north as the sun ever rises. I'm sorry, summer solstice. As far north as the sun would ever rise, sun would ever sit over here. And you see there's a little mark out here. That's the moon extreme opposition. That is the furthest point the moon ever rises to the north or to the, or sets to the south. I also have it down here to the south as well. All right, so on this one, I actually have about 15 different astronomical alignments. When you do your project, you only have to have 3 minutes. Okay. I kind of got crazy, but yeah, hey, gotta go for it. So it's something like that. You want it about this size. You want to be able to explain it. You can make it out of anything you want. I've had people make it out of solid wood. It was really heavy. I've had people make it out of styrofoam. I had one person make it out of candy. A whole bunch of gummy bears and stuff. All right. You can also, if you want to, make it digitally. I've had people do a digital model if you're into 3D modeling, and you just project it and explain it, and rotate the model and show all the alignments within that too. So you got lots of options. We got all the way. This will be due at the very end of the semester. Now, normally I have people work in pairs, okay, on this. So you work in as a group. But with COVID, I know some people probably don't want to work with anybody else. So I'll give you the option here. If you want to work as a pair, that's fine. If you want to do it completely by yourself, that's fine. You just have to do it somehow. Okay. We'll talk about this more as the semester goes on, what kind of project you need to come up with. But that will be part of your grade as well. Okay. All right. So that's the project. There's 3 exams, and there's a final. The final is comprehensive, meaning it covers everything for the whole semester. Then the grading, you can see the homework, the reading assignments, those are the things that I give out. That's 20% of your grade. The 3 tests are 15% each. The final's 20, the project's 15%. I totaled that up to get your grade. I find if somebody does all of it, if you just do it all, you rarely ever fail the class. The only people that ever fail are ones that just don't show up and don't do it. So just remember, this is your job. You're not going to pass, or you're not going to keep a job if you don't show up. I don't know why people think they take a class and then they miss half the class. It's like, come on. You're not going to do that if your employer will fire you right away. This is your job right now. All right. Someday you'll get a job where you're forced to be there all the time. This way you're like, look, I work 3 hours a day. Right? How many hours a day are you in class? 3, maybe 4? Now you have to go study outside of class. But this is probably the freest you'll ever be your whole life. You're working 50 hours, 50 weeks a year, 40 hours a week. You don't have as much freedom as you do right now. All right. Attendance, that's pretty much the same thing, saying that I've been teaching now in college for over 30 years. And the biggest thing I find is that the students that don't show up are the ones that fail. Directly correlated. So just show up every time. All right, if you skip to the back, these are the test dates. I do reserve the right to change them. If I do, I will let you know a couple weeks in advance. But this is what I plan. I usually follow the plan. And I just adjust the test. So if I don't cover as much, I just change the test. It's easier to do than change the test dates. But it is possible if something comes up, like if we have a snow day or something, we might change it. But normally those will be the test dates. And Thus, we're finishing very early this year because we're started a week early. I don't know why, we just all of a sudden, usually we don't start till the day after Martin Luther King, which will be next week. And we don't have spring break. So all of a sudden, we're getting out 2 weeks early. Usually we go to about May 10th. We're getting done. Our last day is April 29th or 30th or something like that. So good news is you're going to be done before almost all the other college students around. So if you're looking for a summer job, you could beat them by 2 weeks. But yeah. Okay, any questions about the syllabus? Great. Now, I also do this different than most teachers I found out. Is I'm going to give you an outline of what we're going to cover in the course. A lot of teachers say, why don't you just put that in the syllabus? I'm like, well, because then I'm not as flexible. So this is what I plan on covering, just to give you an idea of the way the class is going to go. All right, so if you look at this, you can see my astronomical approach to it. So what we're going to start out with, we're going to talk about basically viewing the sky, and we're going to determine cardinal points first. What are cardinal points? North, south, east, and west, right? And we're going to talk about that and how that affects what you see. Everything is determined by your relative position on the Earth and which way you're looking. And then we're going to talk about a couple of places or people that show that. So we're going to talk about the Egyptian pyramids, the Pawnee Indians, the Polynesians. They all were very into north, south, east, and west, and why it was important and how they determined those things. Then we're going to go on and talk about the motion of the sun. Especially, we're going to talk about how high it gets, altitude, at different times of the year, how you calculate that, figure it out. And with that, we're going to talk about Monte Alban and Choqquequirau. I'm sure I pronounced that right, but it's something like that. And Gaoxiaojing, which is actually a Chinese site. Kind of cool too. And then we're going to talk about rising and setting points of the sun, which is the most prominent one that we see. And that's why you see examples. There's gobs of examples. And we'll spend actually the majority of the whole semester talking about the sun position, because that's the biggest thing that we find with our archaeoastronomy sites. Now we're going to talk about the motion of the moon, moon phases. With the moon phase, we're going to talk about the Egyptians again, but this time, instead of talking about the buildings, we're going to talk about their beliefs, their gods, their temples, especially the temple of Dendera, now the symbol. Then we're going to talk about this moon, and the moon is very complicated, much more complicated than the sun. The sun is actually complicated, but the moon makes it even more doubly complicated. And we're going to actually revisit a couple places. Stonehenge, which we talked about earlier, and Chaco Canyon, which was the place we actually would go on our trip. Chaco Canyon is in the northwest there. And we'll talk about what they have to do with that. We actually have a couple of videos we're going to watch during this semester too, to help us understand things. Then we're going to talk about the planets. We don't spend a lot of time on it because there's not a lot of evidence for ancient sites using the planets of the few. Mostly the Mayans, possibly the Incans and the Aztecs. I'll explain more about that later. We know the Mayans did. And now we're going to talk about some calendars, because that's all astronomical to do. All calendars are based on astronomical events. And that's interesting too, especially when we talk about different calendars, especially the Mayan calendar. They're the coolest ones. Anybody that has a triple calendar system going simultaneously is just cool. Questions about any of that? Any questions about the syllabus or any way about how the course is going to be administered? There we go. Did I scare you off? Does everybody want to drop now?
No. Well, I had to go with all the classes.
All right. All right. let's talk astronomy. A lot of this first part, which I'm going to talk about today and on Thursday, we got to get a lot of definitions and understanding down so we're all on the same page. So when I'm saying certain words, you're like, oh, I know what he's talking about there. So basically, when we go outside and look at the sky, what it really looks like is that it's a dome above our head. And this is my astronomer, I call him Herb. Yeah, I called him Herb for 30 years. He just did stuff. The only good thing is in 30 years, I've only had one student that actually named was Herb. He's like, Herb, you're talking about me? I'm like, no, I just picked Herb a long time ago and I just keep using it forever. All right, so if we're in the planetarium, which I usually teach, how many of you have been to the planetarium? Oh, most of you, good. Well, when you're in the planetarium, the ceiling is a dome over your head. Why? Because it was created to mimic the night sky or the sky, right? Planetarium, the whole goal of a planetarium is to be able to project the night sky. And move it forward and backward. And now these planetariums are so sophisticated, all digital, and can do all things. But originally, it was these projectors in the middle that would make the stars and the planets and everything move around. They were kind of cool. I'm thinking in ways they were cooler than the ones now. They aren't. Kind of like saying, oh, the old way was better. Well, nowadays you can fly through the center of black holes and do all kinds of cool things you couldn't do back then. Back then it was pretty much to project the stars and the planets. All right. But when we look at the night sky, okay, or the daytime sky, we see this dome over our head. And the interesting thing, too, about it is all cultures presumed that the Earth was flat. Why? Yeah, because you can't really see the curvature of the Earth, right? The Earth is big enough that creatures of our size can't actually perceive the curve of it. Okay? Now you can, but you have to be in special circumstances. Like if you're an astronaut, you get up high enough, you can actually see the curve of the Earth. But from the Earth, you just really can't tell. You can do it indirectly. And it was the Greeks that started figuring out, oh, it is curved, it is a round, and they actually figured out how you can measure it too. But we're not going to study the Greeks because that's not archaeology anymore. Remember, archaeology are ancient civilizations, that becomes just ancient history. Different here. Okay? So, when we look out there, and we're always going to draw these the same way, we're always going to put north to the left, just for consistency, which means south is to the right. What's on back there, east or west?
West.
Well, I heard them both.
West.
Are you sure?
West.
I hate to tell you, they're right. It's east. West is here. How do you know?
Never eat shredded wheat.
Yeah, but all the letters are there. You can just flip them around.
North is to your left and south is to your right. You're looking east.
Why?
That's just how it is.
Don't you question these things? I don't know why people always assume, oh, that's what the way they taught me. It's like, so why are we doing it that way? Question everything. Why are manhole covers round?
Save money.
You don't ever wonder about these things? Why don't they make them square? There's a reason. It's because a round shape can't fall down the hole. If you have a square shape, you put diagonally, it'll fall in. But a round shape, no matter how you put it there, will never fall down the hole. That's why they make them round. Now you're learning all kinds of, you gotta question everything, right? Okay, so Earth. Here's the Earth, North Pole's here, right? Because we're very northern pole biased, very northern hemisphere biased. Why? And where do most people live? Yeah. 70% of all people live in the northern hemisphere, so we're very northern hemisphere biased, right? Okay. So yes, so we put north up. Now, there are exceptions. Japan, they will actually flip out their thing and put south up. Which, and if you're in Australia, usually south is up too. So it just depends on where you live. But most Europe and us and all that are very northern hemisphere biased. All right, so here's the Earth, North Pole, South Pole. What are the poles? What is the North Pole?
Axis of rotation.
Okay. But what about those people? They didn't think the Earth was spinning. But they still had north. Oh yeah.
Where the stars are.
Where does stars?
Oh yeah. If the Earth isn't spinning, then the stars are spinning around it. And there's a point in the sky where they spin around, right?
Mm-hmm.
If you're in the northern hemisphere, that is the North Pole. Now, how do we define the North Pole? As the rotation axis of the Earth. Okay, so the Earth is spinning, right? Anything spinning, it spins around an axis. It has to. The axis pointing through the Earth defines the North and South Pole. Because otherwise, the Earth is a ball, and you could say, well, you could arbitrarily mark it and count from wherever you wanted, right? In fact, you still could arbitrarily do that. But everybody decided the easiest way to deal with it is to use a reference point the Earth already has. This is the rotation axis, right? Okay. Now, so we're looking down here. You guys are looking at the North Pole. Here is the United States. Here is commerce right up there. Okay. Does the Earth spin this way or this way? Is it counterclockwise if you're looking at it this way? No, he's messing with me again. So I'm in here. Which way did it spin? This way or this way? So you're right. My right. Are you saying it goes this way?
Yeah.
Do you guys agree with it? Yeah.
Are you sure?
Yeah.
Which time's over ahead of us? Which one's behind?
Yes. We'll talk about time zones too. You're right. Trust yourself. It spins this way. How do you know?
I was told to imagine.
You were told. Oh no, we don't believe in that whole stuff, right? Well, think about it.
I was told to imagine that North America was a dragon walking that way.
Now, I want you to think like an ancient person. What observation, what thing could you look at that would determine which way the Earth is rotating? Stars and sun do what? Rise. Where do they rise? To the east. What's that tell you? Yes. What's that tell you? The Earth is spinning from west to east. Okay, we spin this way. So if you're over here, right? If you're a star and I'm spinning here, I'm going to see you come up around the horizon. Then you're going to be at the top, and then you're going to set again. So because all the objects rise in the east, it proves the Earth rotates to the east. Okay, now to then remember, it wasn't the Earth that was spinning; it was the stars that were spinning, right? And which way did they spin? East to west. It still spins the same way, right? It just depends on which thing is spinning. They're still spinning the same way. All right, so we live in Commerce, Texas, in the northern hemisphere. Everything rises in the east, sets in the west, right?
Yes.
Oh, what if you live down here? What if you live in Chile? Does the Earth still spin counterclockwise?
No, I don't think so.
Do objects still rise in the east?
Yeah, why wouldn't it not do it?
I was saying, a little bit split in half. It's just a little bit more.
We don't see as much
Obviously.
sun.
You see, I love asking questions you've never ever thought about, huh?
Yeah.
It's just the seasons.
Yes, of course it does. The Earth can't spin half one way and half the other way. It would rip the Earth apart. Of course it rises in the east. But there's a big difference. Stay with me. Front of the room is south. Behind you is north, right? Which way is east or west? Point to the east. East is this way, right? Right? Yeah. So we're here, Herb right here. This is south, right? So east is to Herb's left. Your left. So east is over there, right? South, east, north, west, right? I feel like I'm flight attendant. All right. When something rises, like the sun, it rises where? East, and it goes, and through the day it goes to the west. So for you, it's going which direction? Left to right. You go to the southern hemisphere, you turn around. Because now the sun doesn't go across the southern sky, the sun goes across the northern sky. Still rises in the east, the east is still here, but you're facing this way. So which way does the sun go? It goes from right to left. So it does mess you up. I've been to the southern hemisphere numerous times. I've been to Australia and South America and stuff too. And it always messes me up because the sun always seems to be going the wrong way. It goes from right to left instead of left to right. Not only that, if you know your constellations, they're all upside down. And seeing Orion upside down is like, what? And the moon upside down? I see this in movies all the time. People don't like going to movies with me because I always say, oh, that's wrong. But they'll put up the moon, but they'll have the moon flipped over. And it's like, you can't do that. You're in California. Now, it is upside down relative to us if you're in the southern hemisphere. But what they do, they don't really care. They just find a picture of the moon, they stick it up there. They don't care which direction it is and whether it's right. They just want the moon up there. So they don't even notice those things. All right. So far, so good. Is this making sense? Which way does the Earth spin? Clockwise or counterclockwise? Which way does the, if you're looking for the North Pole, right? Okay. Which way does the Earth go around the sun?
Counterclockwise.
Clockwise or counterclockwise?
Counterclockwise.
Which way does the moon go around the Earth?
It's opposite.
Which way does Mars go around the sun? Which way does Jupiter go around the sun? Which way does Saturn go around the sun? Which way does Jupiter spin?
Counterclockwise.
Which way does the sun spin?
Counterclockwise.
Yes, every one of them goes counterclockwise, except there's exceptions. Just a message. Why? Because when the whole solar system was formed, it formed out of a spinning gas cloud that was spinning counterclockwise. And that spin got tied up in the planets and the sun, and that's why we're spinning that way. It's because the cloud was spinning that we formed out of, and it was a counterclockwise spinning star, or cloud. That formed a counterclockwise spinning star, our sun, and we were just along for the ride. All right. So, now there are a couple exceptions. Venus actually rotates backwards. But it's so slow, it's a day is longer than a year on Venus. It's almost like not rotating. It's really weird. We think something giant hit it in the past and just messed it up. This is called the horizon. Normally it's called the ground. Okay? But from an astronomical term, we call that the horizon. And ideally, your horizon is perfectly flat. Okay? It works great if you're out in the ocean, because then you get a perfect horizon, because all you see is water all the way around. Here you got buildings and trees and stuff. You don't really get a perfect horizon. But that's the idea, right? Your horizon would be a perfectly flat plane that intersects the sky. Okay? That's the horizon. All right, these are the, put a different color. These are definitely called the cardinal points. Do we have subcardinal points?
Yes.
What are they?
Northeast.
Yeah. Halfway in between, northeast, southeast, southwest, and northwest are what we call subcardinal points. And they're exact positions. They're exactly at between those positions. Those are what's called subcardinal points. Okay. Not important in this class, just added it. All right, if we look straight up, straight over Herb's head, we call this the zenith. So if I say zenith, zenith is
Straight up.
straight up. Okay, so far so good. What is altitude? Astronomical definition.
How far up the sun goes in the sky?
Okay, can you make it more general? Because it doesn't have to be the sun.
How you are, so anything is in the sky?
Is it
How
how
close to zenith
high
is
our atmosphere is?
No, those are definitely different in that. There is altitude as how high up you are from sea level. That's what pilots use. You know, they say, oh, fly at altitude 30,000 feet. That's altitude. That's not an astronomical definition.
Okay.
An astronomical definition is the angle an object is from the horizon to the object. Okay? So we can make that simpler. We can just say how far an object is from the horizon. When we measure, because this is a dome, right? Everything is measured in angles. You don't ever say, oh, you know, you don't go outside and there's a star here and a star. How far apart is that? And you go, I don't know, it's about 2 feet. That doesn't make any sense, does it? What you're really doing is measuring the angle between the two objects. Same thing here. What is the altitude of the zenith?
90.
Okay, good, because if you go from the horizon like this, you make a 90-degree angle. What's the altitude of the horizon?
180?
Zero.
Or zero?
Zero, right? Because you're right on the horizon. Can you have those are all positive altitude. Can you have a negative altitude?
If you're in south,
Yeah, can't
is it
see it.
southern hemisphere?
Yeah, so if you go, it's past that horizon.
If it's below the horizon, it's negative. Yes, you can actually see that sometimes. If you're on top of a mountain, you can actually see below horizontal. Okay? So that's kind of cool. Also, astronomers use it a lot too, because when we're tracking things, like you say, oh, I want to know when Jupiter's rise is, you plug it in your computer, it'll say, oh, Jupiter's at an altitude of negative 14 degrees or something like that. So you know it's 14 degrees below the horizon, and then I'll get less and less until it rises, where its altitude goes to 0, and then it gets higher and goes down.
Would you say the zenith was 75 degrees?
I said the altitude of the zenith is 90.
Oh.
90 degrees, right? Because this is 180 and it's exactly halfway.
Oh, yeah.
My picture's not exactly halfway, but imagine it was drawn right. All right. Okay. Now, let's talk about angles. Don't transpose the E now. We're not talking about angels. Different class. Angles. What's an angle?
The exact point between two objects? Degree between two objects?
Okay. Measure of the.
Degree between two objects?
Displacement.
Yes.
Yeah. It's not as easy as it is to think about, right?
Angle.
Technically, in geometry class,
Oh, from up there, yeah.
it's the arc difference between two rays connected at a vertex. Like, what? Yeah, you don't have to know all that kind of thing. You just got to say, everybody knows what an angle is, right? There's always a point, and the angle is the distance between it, right? We usually measure angles in degrees. How many degrees in a circle?
160.
Why?
Why is it 360 degrees in a circle?
Yeah, why not 22.9?
Because it goes all the way around.
Oh yeah, but why 360? Who decided it? Why are we forced to use it? Don't you ever see, you gotta go question anything. You're like, oh, somebody told me it's 360. It just is.
That is true.
There's a reason for everything. You gotta figure it out. Do some research. 360 came from the Egyptians. Why? 360 is close to what number that's important in astronomy was?
365.
Which is what?
How many days in a year?
Oh, yeah. Why do we got 60 seconds in a minute?
Easy to provide.
60 minutes in an hour? 24 hours in a day? Guess what? That all came from the Egyptians.
Okay, so there's 360.
We probably stole from the Babylonians, but we're giving credit to the Egyptians. To the Egyptians, 60 was a very special number, which is why we have a base 60 time system. Ever wondered why that? It's like, that's crazy. Yeah, it is. We do a lot of crazy things just because it's always been done and nobody ever questions it. So they were the ones that said, oh, there's 60 seconds in a minute, there's 60 minutes in an hour, and he split a day into 12 hours of day and 12 hours of night, which we know changes throughout the year, and they knew that too. Okay? But is 365 divided by 60? Oh no, that would be a problem. 60 is a perfect number. So let's make it 360. They knew a year was 365 days. But they didn't want to use 365 as their measure because it's not divisible, it's not easy to use, right? And it's not 60s, it's not perfect. It shows how your bias changes things, right? Do we use that today? Oh, absolutely. All right. 360 degrees came because the Egyptians realized that it took the sun 365 days to go around to the same spot in the sky. Remember, it was the sun moving, not us going around it. It took the sun 365 days to go around the sky back to the same point. They decided to call it 360, and they realized that the sun moves about 1 degree a day. See, it's all based on astronomy. That's where 360 came from, which we still use today, right? All right. And yes, they also gave us the time system. You know, when they went to the metric system, when the French invented the metric system, they wanted to change time too. So we didn't have the 60-60 stuff. They said, oh, this should be base 10 or base 100. So they wanted each minute to have 100 seconds. And each hour to have 100 minutes. And each day would be about 10 hours long instead of 24 hours. And it's based on hundreds and tens. It would have made total sense. But everything, no, that's confusing. Everything's confusing until you learn it the first time, right? If you were taught that from the beginning, it wouldn't make total sense, right? Where did 1 second come from? The length of time 1 second? Do we know? Probably came from several sources, but there's one obvious one. The Egyptians, but what were the Egyptians? What physical phenomena happens about once a second? The what?
Breathing or blinking?
No, but you're right. It has to do with humans. What do I do when I do this? An average resting heartbeat is about 60 beats per minute, right? Or about once a second. Now, we don't know that that's exactly what they did. There was no written thing that said, oh, they did this. But it's guessed that that's a possibility. All right. So angles, 360 degrees. Ooh, I'm running out of time. The problem is, in astronomy, a degree is too big. So if I have a 1 degree angle, okay, that's way out of proportion. But astronomers, we want to split that into smaller angles. So we split that into 60 smaller angles. Because we're still obsessed with 60. And we call each one of these smaller ones an arc minute. Or we can say that there's 60 arc minutes is equal to 1 degree. Or 1 arc minute is 1/60th of a degree. And then for astronomers, that's still too big a number, too big an angle, because we want to measure even smaller than that. So we're going to take each of these arc minutes and we're going to split it into 60 more. By the way, we often write arc minutes with a single slash. Okay, so if you see 60 with a single slash, that means 60 arc minutes. So we split each of these arc minutes up into 60
Arc seconds.
seconds, of course. Remember, we're astronomers, we're not creative. And instead of one slash, you do two slashes. So 60 arc seconds is equal to 60 arc minutes, which is equal to 1 arc minute, right? Which is 1/60th of a degree. So how many arc minutes, how many arc seconds in a degree? This is not higher math, people. If there's 60 arc minutes, how many?
3,600.
Yeah, there's 60 arc seconds in each of those, right? You just multiply it.
Yeah.
So 60 times 60, there are 3,600 arc seconds in 1 degree. Right? All right. Hold your hand up like this, thumb on the top, arm extended. That, from the bottom of your hand to the top of your thumb, is about 10 degrees. You can test it, right? If you go 10 and you hold it there, you go like that, 20, 30, 40. If you get up to 90 straight overhead, that's how big your hand is, right? It's a rough approximation. Okay. Now, that means each of your fingers is about 2 degrees. Your pinky is probably about 1.5. Okay. Go outside after class. Hold your arm extended. Put up your pinky. Can you cover the sun completely? How big is the sun? Is it bigger than 1.5 degrees across? No. Anybody know? The sun is about 30 arc minutes across, which is half a degree. So can your pinky cover it, even with your arm extended?
Yeah.
Not only can it cover it once, it can cover it 3 times. But it seems like the sun's a whole lot bigger, right? That's because the sun's really bright. And our brain associates bright with big. So we think, oh, it's bright, it must be big. But it really isn't that big. Okay? Now don't stare at the sun, bad for your eyes. Okay? So, it's gonna be how big is the full moon?
No. 10 arc minutes.
Seems bigger.
What happens in a total solar eclipse?
Oh,
Yeah,
so it's
the moon covers-
They're the same size! Son of a gun! Guess what? On the sky, the actual area of the sun is 400 times bigger than the moon. Take 400 moons to fit across the surface of the sun. But the moon is almost exactly 400 times closer. So in our sky, they are nearly the exact same size. Guess what? That is just pure luck. Because right now, the moon is getting further away from us. And as it gets further away from us, it's getting smaller. So if we lived several million years from now, the moon would never cover the sun in an eclipse. We just live at the right time. It's going to take a long time, probably more like 100-something years, but you have to live at the right time. If we lived several billion years ago, the moon was much bigger than the sun because the moon was a lot closer. The moon is slowly getting further away from us. Not only that, it's stealing our angular momentum. It's slowing us down. A day now of 24 hours, 3 billion years ago, a day was about 14 hours. So the Earth is slowing down. The moon is actually stealing our angular momentum. Crazy. All right, I'm way out of time. By 2 minutes. All right, I'll see you on Thursday.
Yes, sir.
Bring your compass and straight edge.